let's actually get to solve this. This is very similar to the example that we solved last time. If you recall, the example that we solved last time had this, these three zeros, and you had a non-zero thing here. And apparently, you really need three of them to be zeros to have an easy solution. If you have more than one being non-zero, then you have to have some more elaborate strategy, which I'll explain later. It's not too hard, but it's more work. Okay. All right, so in this case, what we are going to do is we are going to leave out the non-zero one and just solve these. Okay, let's try to solve them using separation of variables. The step one would be to assume that, or you're trying to find all the possible solutions of the Laplace equation and the three boundary conditions in the form of a function of x times a function of y. Let's plug this into here. Remember, this is u xx plus u yy. That's what the Laplace means. So if you differentiate this one twice in the x, twice with respect to x, then you get x double prime y. Then plus, if you take this and differentiate twice with respect to y, you get x y double prime equal to 0. Move this to the other side. And then you divide both sides by xy, so that this cancels away, and then this cancels away. So you get x double prime over x equal to negative y double prime over y. Okay. Again, we use the standard argument that the left side is a function of x only, the right side is a function of y only. That means the only way they could be equal is if they're equal to a constant function, right? A function of x can only equal to a function of y if they're both constant functions. So it's very similar to our last time, except in our case, the ones that are going to give us two conditions is this one. If you look at this one, let's write down what that means in terms of x and y. This means x of x of y of 0 is 0, and also x of x y of 5 is also 0. These are both zeros. And whenever you have two things multiplied equal to 0, either one has to be 0, right? But we don't want x of x to be 0. Why is that? Because if x of x is 0, then u would be just 0 for every x and y. And the goal of all this work is to find non-trivial solutions that satisfy these. So we can find all these building blocks for the general solution, right? And we wouldn't be able to achieve that if this just becomes 0. So this would imply that y of 0 and y of 5 should be 0. And therefore you see that the Sturm-Liouville problem that you would be using would be not in terms of x, like our example last time. Instead, there will be an example. It will be a Sturm-Liouville for y, right? So in this case, we used to set this equal to negative lambda whenever we solve the heat equation, right? Here, it's in this case we need the lambda. Okay?
Is it because there's a negative on one?
Yeah, because of this negative in front, we want the plus lambda. So that if we take this and multiply by y, or multiply by negative y, you get y double prime equals to negative lambda y. And then you move this to the other side, you get y double prime plus lambda y, which is the usual form of the Sturm-Liouville problem, right? So the Sturm-Liouville problem of this, with these boundary conditions, these two, are solved. If we work out the Sturm-Liouville problem, we see that the only non-trivial solutions of this equation that would satisfy this would be, guess what? Which ones? Sines or cosines?
Sine.
It'll be sines, right? Because the values at the endpoints are 0. If the derivatives are 0, then it's cosine, right? But here, the value themselves are 0, so the only solutions are y of y would be sine of n pi over 5
X.
y,
Okay.
y, with the lambda values being what?
N squared,
Pi squared over 25, 5 squared, right? So you just take this value and you square that. That's what you get. You can easily see that if you replace lambda by this value and plug that in, these do become solutions. So that's how you can understand what's happening if you're not sure of the Sturm-Liouville. Okay, and this will be true for any n starting from 1, right? So, in fact, you don't get a single solution, you get infinitely many solutions. Now, since we got the values for lambda, let's plug that back in and solve for x. So, x double prime, if I multiply the x to the other side, you get x double prime equals to lambda times x. And then, if I replace lambda by n squared pi squared over 25 and move it to the left side, you get x double prime minus lambda, but instead of lambda you get n squared pi squared over 25, capital X equal to 0. And this is a second order constant coefficient differential equation, which can be solved by using the characteristic equation. Set that equal to 0, and then you get r equals to plus minus n pi over 5, which says that your x of x must be c1 times e to the n pi over 5x plus c2 times e to the negative n pi over 5. So this is what you get from these, right? However, that's often not the form that you want. We learned that, right? Yeah. Instead of these, what do we use? The more convenient functions are. What are the functions that's more convenient than the exponential functions?
Cosh and sinh.
Yeah, cosh and sinh, right? So the hyperbolic sine and cosine functions. Yeah. So you have these cosine hyperbolic of x equals to e to the x plus e to the negative x over 2, and sine hyperbolic of x equals to e to the x minus e to the negative x over 2. And you can just write down x of x as c1 times this thing plus c2 times sine hyperbolic of x. Oh, with instead of x, you want to plug in n pi over 5x, n pi over 5x. And just imagine what's going to happen if you replace this by this one and you replace by that one. Then, I'll do a quick calculation. C1 e to the n pi over 5x plus e to the negative n pi over 5x over 2 plus C2 e to the n pi over 5x minus e to the negative n pi over 5x over 2, so that if you gather only the e to the n pi over 5x, you get C1 over 2 plus C2 over 2 e to the n pi over 5x plus C1 minus C2 over 2 e to the negative n pi over 5x, so that if you if you call this C1 prime and C2 prime and let C1 prime be this quantity here, C2 prime be this quantity, then they're the same thing, right? C1 and C2 are just arbitrary constants. So are C1 prime and C2 prime. So they're the same thing. So writing it this way or this way, it doesn't matter. It's the same thing. Yeah. So we like this one better because you'll see that immediately one of them just cancel out. The formulas are simpler. However, today, because we are trying to use this condition, we haven't made use of this condition yet, right? We want to plug in x equals to 4 and get 0. We are going to do one more slight change. So instead of writing it this way, we're going to rewrite x of x. And you'll see why. So instead of this, we're going to say x of x is C1 cosine hyperbolic of n pi over 5 x minus 4 plus C2 sine hyperbolic n pi over 5 x minus 4. We want to write it like this because if you plug in 4, what's cosh of 0? We did that last time, right? Cosh of 0 is?
0.
No.
1.
Yeah. And sinh of 0 is 0, right? So, see, this condition, just like from the same argument as before, this condition is going to say that x of 4 has to be 0 because y of y can't be 0. So if x of 4 is 0, you plug in 4 and you get 0 on the left side, whereas on the right side you get c1 times cosh of 0 plus c2 times sinh of 0. What do you get? This sinh of 0 is 0, so that's gone. This is 1, so that your conclusion is that C1 must be 0. And that gives you a very simple formula for x of x, which is that x of x must be equal to C2, or some constant times sine hyperbolic of n pi over 5 x minus 4. Okay? You want to write like that. Is that okay? Yes?
Can you explain why you can change x to x minus 4?
I mean, you can, so, again, you can rewrite the definition. It takes a while, but let's see, cosine hyperbolic of n pi over 5 x minus 4 is e to the n pi, well, this is n pi over 5x minus 4 n pi over 5 plus e to the n pi over 5x, actually minus plus 4 n pi over 5 over 2. Is that okay? If I just use the definition that cosine hyperbolic of x is e to the x plus e to the negative x over 2. But then, think about what this is. This is just e to the negative 4n pi over 5, which is some constant, right? That's some constant that for a fixed value of n, this is just a number, right? And the same thing here. This is just plus e to the n 4n pi over 5, which is a number. X's are here. Okay?
But this
So
consists in n, right?
it depends on n, but we're fixing n for each fixed n, right? For each fixed n, x is a function of x, and
It doesn't matter which n is 5.
yeah. So for each fixed n, this is a number, that's a number. So if you have like c1 in front, and the sinh of x, c2 in front, and then you multiply them out, you can again make the same argument that c1 prime will be some mixture with some strain coefficients. It's just more Fourier than before. That's all it is. Yes?
I don't know why you put x minus 4 on it.
Oh, because I want one of them to be 0. If I don't have x minus 4, what would you get?
X.
If I plug in 4, I get cosh of 4 n pi over 5, which I have no idea, but C1 will still be there, right?
Oh.
And C2 will still be there. I don't like that.
But if you're doing that, if you plug in 0, that's
If you can't plug in 0. 0 is not 0.
Oh.
You want to plug in 4.
It depends on which.
Yeah, you're forced to plug in 4.
It depends on what you.
Well, okay, so since you guys are still unhappy with that,
So since you're saying e to the 4n pi over 5 is a constant, I mean it's only going to be a constant. So C1 only the value of C1 will change. So it doesn't really matter, right?
okay,
It's just
I
easier
think
way
you
to solve it, right?
all right, it's getting too complicated. Let's try the other way. Let's say we didn't do any of that. Let's just start with this one. Let's see what we get. We get let's say x of x is C1 e to the n pi over 5x plus C2 e to the negative n pi over 5x. Okay, and we say 0 has to equal to x of 4. X of 4 has to be 0, right? Okay? So if x of 4 is 0, then you get C1 e to the n pi over 5, and you're plugging in 4, right? Then plus C2 e to the negative n pi over 5 x. No, times 4. Is that okay? I want that to be 0, right? Is that okay? All right. So here's another thing that we could do. Is just redefine. Let's just call this the original C1 and C2 as C1 prime and C2 prime, right? And then say C1 prime is e to the negative 20 n pi, no, 4 n pi over 5 times C1 for some other constant, because some arbitrary constant, right? This is some constant, that's some constant, right? For a fixed n. You can do that, right? Agreed? All right. And then C2 prime as e to the positive 4 n pi over 5 C2. Then the nice thing about this is if you plug that in, you get 0 equals to, what do you get? This, if you replace this by this, what do you get? This and this will multiply to what?
1.
1. So you get what? It's just C1, right?
Yep.
Is that good? All right. And then what would you get here?
C2.
Just C2, right? Just C2. Okay? Is that good? All right. So C2 is just equals to negative C1. All right? So you can rewrite this as negative C1 e to the 4 n pi over 5. And then just plug these C1 prime and C2 prime over to the original one, because I know that that should be the general solution satisfying x of 4 equal to 0, right? Let's see what happens then. Then this is what you get. You get x of x equal to C1 prime is this thing, so it's C1 times e to the negative 4 n pi over 5 times e to the n pi over 5x plus minus C1 e to the, this side is plus, so positive 4 n pi over 5 e to the negative n pi over 5x. So far so good? Is that okay? All right. And then we can rewrite this as 2C1, okay, 2C1. And then you can put this into single exponent, right? So we can write this as e to the n pi over 5x minus 4n pi over 5. And then minus e to the negative n pi over 5x minus 4n pi over 5. All right, so what am I trying to say? What is this? What is this thing inside? You don't see it?
Isn't
So basically you're saying this is
separable?
cosine h.
This is,
This
look,
is-
sine h, sinh of x is what? By definition, this is e to the x minus e to the negative x over 2, right?
yeah.
So
Oh, yeah,
if you plug in into x n pi over 4, n pi over 5, x minus 4, if you replace this x by this much, you get exactly this. Do you agree? Yeah, so we know that x of x must be some arbitrary constant times sine hyperbolic of this thing. Okay? So this is longer, that's why I didn't want to explain it this way, but because so many of you were like very skeptical that you could represent things in terms of instead of n pi over 5x, you can use this. I had to go explain it this way, but it's, at the end of the day, it's the same thing. What's the conclusion here? The conclusion is that x of x must equal to some constant. 2c1 is some constant. Okay, so some constant times sine hyperbolic of n pi over 5 x minus 4. That's our conclusion, whatever you do. But please don't do it this way. This is like a really convoluted way of doing things. The better way is what I showed you. Rather than writing down your solution in that way, you just write your solution in the form of c1 cosine hyperbolic n pi over 5 x minus 4 plus c2 sine hyperbolic n pi over 5 x minus 4, and then you apply this condition, you'll see that c1 has to be 0, and you immediately get that. That's a lot faster if you just trust that these two are equivalent. Okay? Is that okay? Are you guys convinced here? Okay, so fully convinced. All right. Okay. So because I now have the x and then y, we know that in general the form is uxy. Well, I guess I can go back to the original one here. So this one says that uxy has to look like a function of x should be some constant times sine hyperbolic n pi over 5 x minus 4 times, for the y's, it's sine of n pi over 5 of y. Okay? So that's what we get as the answer to step 1. Is that okay? All right. Now, how do you find the general solution of these then? Because each of these are solutions for n equals to 1, 2, 3, 4, 5, and so on and so on. So what do?
Linear combination.
Yeah, you just take the linear combinations of them. Okay. So you promote this c to be cn, right? And then you go from n equals to 1 to infinity. Okay. So this is going to satisfy all the conditions except for u of 0, y equals to y, right? So now it's step 2, right? What's step 2?
Use the other one.
Yeah, you use the remaining one. You plug in 0 into x, and then you get y equals to u of 0y. That's our condition here. But then if you plug in 0 over here, you get summation n equals to 1 through infinity of Cn sine hyperbolic of negative 4 n pi over 5 times sine of n pi over 5y. Okay, so if I plug in 0 here, that goes away, and negative 4 times n pi over 5 will be negative 4 n pi over 5. And I didn't change anything else, that's what you get. And again, even if this has an n there, for each fixed n, this is a number, right? So you really have a number times a function of y, a sine of something, okay? And you're trying to express y as sum of sine functions. What is that called?
Fourier sine series.
Yes, that's called the Fourier sine series. So now let's try to apply the Fourier sine series. Right, Fourier sine series has the formula Bn equals to 2 over L integral from 0 to L f of x times sine n pi over Lx dx. In our case, since these are functions of y rather than function of x, we have Bn equals to 2 over, since I see a 5 here in place of L, the L must be 5, 0 to 5. It's f of y, and our f of y is y, times sine n pi over 5 y dy. Okay, so that's what we have to compute. And let's do tabular integration. Y differentiates to 1, 1 differentiates to 0. I put sine n pi over 5x, integrating, I get 5 over n pi with a minus, cosine n pi over 5x. Integrate this one more time, you get negative 25 over n squared pi squared sine n pi over 5x plus minus plus, and then the result of the integral is this plus this, right? However, we know that the sine functions, when you plug in the boundary points, you get zeros. So the only thing that doesn't create negatives will be equals to, what is it? Negative 5y over n pi cosine 2 over 5. Cosine n pi over 5 y, and then you have to plug in y as 5 and y as 0. Now when you plug in 0, this is 1, but you have a 0 here as well, so you get 0 if you plug in 0. So the only non-zero thing that you get out of this big computation is when y equals to 5 is plugged in here, which is, what's that?
Negative 1 over n.
Yeah, so 5 and 5 cancels, we get cosine n pi, which is negative 1 to the nth power, right? And then 5 goes here as well. Don't forget this one. This one also has y, so that 5 should go there. But that 5 is going to cancel with this 5. So you just get 2 times negative 5, which is negative 10 over n pi. So that's what you get. And the outcome of this calculation is saying that y has to equal to summation from 1 through infinity of negative 10 over n pi, negative 1 to the nth power, sine of n pi over 5y. And that has to equal to this one, right? And if you compare this series with that series, you see that this unknown constants are exactly these. Is that okay? All right. Now, one more thing. I explained that the definition of the sine hyperbolic and cosine hyperbolic are the even and odd parts of the exponential function. Yeah, I wish I had time to explain that as well, but any function can be split into the even part and the odd part of the function. Don't write this, it's going to just confuse you later when you see it. But you can see that if you simplify the right side, these two cancel away, so you get this for any function, right? But you can see that this is an even function, whereas this is an odd function. Okay? If you draw the graph of this is symmetric with respect to the y-axis, and this one's symmetric with respect to the origin. So you can take any function and express it as an even part plus the odd part of the function. And if you replace f by e to the x, then you get exactly this as the cosine hyperbolic and this as the sine hyperbolic. Okay, so it's really even and odd part of the exponential function, and it really helps us in these cases because I know that sine hyperbolic is the odd part. So if you have a minus, what can you do? You can bring it outside. That's what odd functions do, right? If you have a minus, you can bring it outside. What happens if this was an even function? It will just ignore it. It will consume away the negative, right? Okay, so even function means f of negative x is same as f of x, and odd function means f of negative x is negative f of x. So because of that, you can bring the minus outside. So here's what we get. By comparing the two sides, we have, this can be written as negative Cn sine hyperbolic of n pi over, 4n pi over 5 equal to negative 10 over n pi, negative 1 to the nth power, and then you can now cancel away the minus, bring this down, divide by that, and we get Cn as 10 over n pi times sine hyperbolic of 4n pi over 5 times negative 1 to the nth power. Is that okay? Yeah. So we're almost there. What's the answer now?
Plug in everything together.
Yeah, you just plug everything back in, and the final answer would be, ux, so the final answer would be uxy equals to summation n equals to 1 through infinity of that horrible looking thing, 10 over n pi sine hyperbolic n pi over 4n pi over 5 times negative 1 to the nth power sine hyperbolic of n pi over 5x minus 4 sine of n pi over 5y. Okay, so that's the final answer.